As I said in class, I have a little bit of a problem with the way the textbook and the support, public support materials approach curves in space as well as quadric surfaces. Generally, they create graphs that look like graphs that are done by graphing calculators. Okay, now there's nothing wrong with those graphs, but the thing that really disturbs me is that nobody's really asked to do much construction of graphs, and as a result, don't have a really good feel for the way these functions behave. You get a bunch of formulas, you get a bunch of abstract proofs, you apply the formulas without really understanding the proofs or understanding the motion. Another thing is a lot of the examples give you very strange looking graphs. They're actually kind of hard to see, hard to read, hard to see exactly where the graph is. Involve functions that, as far as I can fathom, I really, I don't know everything, but I really have a hard time seeing how some of these functions would ever arise in any important application. So I want to just create graphs and explore graphs and some of the properties of some simple functions that are not all that difficult to understand or to at least make a good attempt to graph. So, one, of course, is the helix that we saw in the preceding class. Okay, so we start with just a basic idea that not everybody understands as well as they should, because I'm not sure what happens to people in second semester pre-calculus courses or equivalent courses, but they very seldom come out understanding circular model of trigonometric functions, which is foundational. Okay, so here we go. Here's a unit circle, a circle of radius 1. We know that for any point on the circle we can have a vector from the origin out to that point. That'll be our r of theta vector, where theta is the angle of the vector with respect to the positive x-axis, and positive in the counterclockwise direction, negative in the clockwise direction. With that convention, the, in my opinion, best definition of sine theta and cosine theta is in terms of this picture, where cosine theta and sine theta are the coordinates of the point on the circle for which the vector makes angle theta. Okay, so the cosine theta is here, sine theta is here. If you're going to visualize sines and cosines, this is much better and easier than trying to visualize it with triangles, although for some people that might be better, and the triangle definition is also good, but it's not as general. Okay, I mean, you've got a right triangle within here, right? Right triangle with legs equal to the cosine and the sine, so that the magnitude of this vector is guaranteed to be 1, since cosine squared theta plus sine squared theta equals 1. Okay, so anyhow, coordinates of the point when the vectors at angle theta, a unit vector at angle theta, are cosine theta and sine theta. Now, if theta changes due to some function, in other words, if theta is, let's say, a function of time, t, then this thing will begin moving around, or at least move upon the circle, and trace out a path on the arc of the circle. If theta equals omega t, then r of t is cosine omega t plus sine of omega t. If omega is a constant, then we have a straightforward interpretation. Okay? So let's just expand this a little bit and then talk about the effect of omega. If r of t is a times the cosine of omega ti plus sine of omega tj, in other words, a times this, that just increases the length of the vector from 1 to a. Everything gets multiplied by a, so the components of this vector would be multiplied by a, so the circle would have radius a. So this represents motion on the arc of a circle of radius a. Okay, now if omega is a constant, then and a positive constant, then when t is 0, we're at position 0, and then as t increases, theta, which is equal to omega t, is going to increase, and we're going to eventually go around the circle. Turns out then that we sweep out a circle of radius a. The period of the motion is t equals 2 pi over omega. Why is that? Because when omega t changes for both of these functions by 2 pi, you've completed a circle. The theta goes from 0 to 2 pi. The cosine goes from 1 to 0 to negative 1, back through 0 and back to 1. So we go around the circle. This point, this projection, follows this path. The sine does the same thing, except it starts at 0, because of course when t equals 0, we're here on the circle, and the sine is going to be 0. But then it's going to go up to 1, down to 0, to negative 1, and back to 0. And if this is something you don't understand in the depths of your soul, again, something was deficient in your trigonometry or pre-calculus course, and it might have been you. Okay? It might have been that the course allowed you to get through successfully without really understanding anything, and then it's kind of on the course. And a lot of it's just on the way the curriculum is designed in this country, and the way we end up having to shortcut things because we're putting too many students in advanced courses when they can't do them or won't do them. More often the former than the latter than the former. Okay, well, I get off my soapbox, but period of motion around the circle is 2 pi over omega, because if your time t changes by 2 pi over omega, then omega t changes by omega times 2 pi over omega, which is 2 pi. And 2 pi is the angle that completes a circuit around the circle. So this is a formula you can memorize. Big T stands for the period of motion, and you can memorize this, but if you're normal, you'll never get you'll never memorize it correctly. And it's better to understand why it is. If the period is how much t has to change so that omega t changes by 2 pi. If you understand that, then you can always figure this out. In any case, either way, I make the comment that it's this so that omega t equals omega times big T. Omega times the period is 2 pi, which we need because that's what it takes the sine and cosine to complete their cycles. It's what it takes for theta to get all the way around the circle. Okay, well, there's that model. Okay, now we ask, okay, well, let's, instead of a constant times this, let's say we have t times the cosine omega ti plus sine omega tj. Okay, well, cosine and the sine both go through complete cycles, so your vector, the direction of your vector, goes all the way from 0 to 2 pi as little t goes from 0 to the period big T, but it's not really, well, it's a period, but the motions are not actually periodic. Okay, the motion of the direction is periodic, but as we'll see, the motion isn't really periodic. Okay, so as t goes from 0 to big T, then the angle goes from 0 to 2 pi. However, the radius of the circle on which this thing is moving keeps changing because the radius of the circle is the coefficient of this expression. Just as when you have a constant number a in front of this thing, you're moving on a circle of radius a, and that circle stays the same. What happens here is the radius of your circle is t, and t starts at 0, and for the first period of theta at least, ends at capital T. Now it can keep moving, as we'll see down here, but so our position moves from a circle of radius 0 to a circle of radius t. So we can have a circle of radius 0, which is just really up the point, that would be the origin, out to radius big T, which is depicted here. I've got 4 concentric circles. The outermost circle has radius t. So when I labeled this, it made sense. The t equals t. When t equals t, you're on this circle, but you don't stay on this circle. You move to a bigger circle. You keep moving to a bigger circle as you go around, and you end up with this spiral shape. For the first period of the angle, you start here and you move around to here. Of course, t can keep going past big T, and you can go around through another cycle of theta with your distance from the origin constantly increasing. So I've drawn 4 concentric circles, actually a 5th one. Here's the first, second, third, fourth that I drew, and this circle here corresponds to t over 4. Okay, so I'll just lightly point to that. And then this one to t over 2, this one to 3/4 of t, and this one to t. When the time is big T over 4, your angle is going to be pi over 2. You're going to be on the y-axis. And your radius, the length of your vector is going to be t, which is big T over 4. So you're going to be at this point on this circle of radius big T over 4 at the angular position pi over 2. That's this point here. And then when little t equals big T over 2, you're going to be on this circle, and the angle is going to be pi. Then you'll be on the circle of radius 3/4 t, and finally on the circle of radius t as the angle goes to 3 pi over 2 and 2 pi. I did draw a small circle in here that will correspond to t over 8. So I have room here. I can go kind of do this. Okay, so that would be this little circle in here. And we needed that to see how we get from here to here. From the point on the origin to the point on the y-axis. We come out in the direction pi over 4. And we come out a distance of big T over 8, which is half the radius of this circle here. So we're in this little circle, we'll be on this circle, we'll be at this angle. And if you understand polar coordinates, all this is easy to understand. If you don't, you really got to go back and work through it again. Everybody did well on the parametric equations and the review of the prerequisite chapter. So I assume everybody more or less knows this. Okay, so we're basically doing a polar spiral here. Now, I drew these little vectors here. Okay, these vectors could represent speeds, how fast you're moving on the circle, or they could represent unit tangent vectors. This is because, well, no, actually they can't represent speeds because the speeds keep increasing. These are unit tangent vectors. And I mentioned that if you draw 2 unit tangent vectors, let's say one for this point and one for this point, and put them together with the same initial point, then the change in the unit tangent vector will be from the first to the second. That'll be this vector here. Makes a little isosceles triangle with these 2 unit tangent vectors. It's isosceles because unit tangent vectors are of length 1. They have the same length. This little vector here is important. We'll come back to it in a little while. It's the change in the unit tangent vector. So it might help if I label these. So these are unit tangent vectors. And this little thing here is a change in unit tangent vector from a vector that's in this direction to a vector that's in this direction. And this is important to note it. It's an isosceles. The three vectors make an isosceles triangle. Now, yeah, we'll move on to another model, another definition. Okay, here's another vector function, r of t. Cosine of pi t squared I plus sine of pi t squared j. How does this work? Well, we're moving on the unit circle because the magnitude of r is just the square root of the cosine squared of, I've got omega t here, let me fix it. In this case it would be pi t squared. Well, that's the cosine of an angle plus the square root of a cosine plus the square of a sine of the same angle. Pythagorean identity, it's 1. The square root of 1 is 1. So the magnitude of r of t is 1. The magnitude of r prime of t being here, we just take the derivative. The inner function is pi t squared, has derivative 2 pi t. And then we have the derivative of the cosine and the sine. We get 2 pi t factor from the chain rule for each of these, and we get a negative sign from the cosine and a cosine from the sine, and right there is your derivative. Might be a little hard to read, I'll read it to you. It's 2 pi t times the quantity negative sine of pi t squared times the I vector, plus the cosine of pi t squared times the I vector. Now, 2 pi t is multiplied by the whole quantity, so it's multiplied by each, by the sine as well as by the cosine. And I wrote I where I should have written j here. Pretty sure everybody knew what I meant. So there we have it. Now, by the geometry of the circle, the r prime vectors, and r prime is always tangent to your path, so it's tangent to the circle, so the r prime vectors are all perpendicular to radial vectors. The vector from the origin out to the point is perpendicular to the tangent vector, which means that the velocity is perpendicular to the radial vector. The velocity, the magnitude of r prime, if you just write it out, you're going to get 2 pi t. And that's equal to the magnitude of the velocity, which is the speed. So, as t increases, the speed of motion around this circle increases. And I've shown that by vectors that get longer and longer. Maybe they should have gotten longer in here, but there they are. And they're intended to show that the speed is increasing. You could draw a better picture. This motion isn't periodic. The motion of theta isn't periodic. Nothing about the motion is periodic. So we can't talk about the period of motion. The first cycle is completed when pi t squared is 2 pi. Okay, at t equals 0, we're here, and when pi t squared is 2 pi, we're back at this point. Okay, so the t is approximately equal to the square root of 2, which is 1.4. 1.4 units of whatever the time is measured in. If time is measured in seconds, then it'd be 1.4 seconds. So the first period takes 1.4 seconds, let's say, or 1.4 time units, whichever way you want to think of it. Okay, the second cycle occurs when pi t squared, it is completed when pi t squared is 4 pi, which occurs when t equals 2. Now, you notice that the second cycle didn't take 2 units of time. The second cycle started when the first cycle ended at 1.4 approximately 1.4 units of time, and ended at 2 seconds. So the first cycle takes 1.4 seconds. The second cycle is then completed when t equals 2 seconds, which is only 6/10 of a second later. So the second cycle takes only 6/10 of a second. And the third cycle is completed when pi t squared equals 6 pi. The square root of 6 is about 2.45. Maybe it's 2.44, 2.46. I don't want to think that hard right now. But yeah, 25 squared is 625, 24 squared is 576. So it's pretty close to 2.45. Take the curvature in, and it might be 2.44. Okay. In any case, I'm using 2.45. Okay, which means that the second cycle occurs between t equals 2 and 2.45. It takes 0.45 seconds or time units for the third cycle to complete. So cycles complete in respectively 1.4, 0.6, and 0.45 units of time. So you're going around this circle, then you're going around much faster than that. The velocity vectors do this. The unit tangent vectors, though, each unit tangent vector is the velocity vector divided by its magnitude, which brings it down to a unit vector. So we have unit tangent vectors that maybe look like this. All the same length. And between any two equally spaced unit tangent vectors, the change in the unit tangent vector, that third side of the triangle made by the two vectors that we looked at earlier, is the same, provided these are separated by the same distance, and that's going to be important. Okay, now look at another function. We're going to go into 3 dimensions. R of t is cosine pi t times I plus a sine of pi t times j plus t times k. Now we did this in a previous class. I'm not sure it was exactly the same function. I'm not sure I had pi from the value of omega, but so be it. Sticking with pi t here because the period is still 2, and that's a convenient period to work with. Okay, so the projection of the path down into the xy plane, well, you just take the k off, and now you've projected all these points down to the xy plane, and you get a unit circle again. Every point on the path lies above this unit circle. So we say the unit circle is a projection of the path. And again, the I and j components guarantee that in the xy plane this is on the unit circle, and at this point lies above or below the unit circle. T could be negative, so you could have this thing extending down below the xy plane. When t equals 0, tk is 0, you're here. Now, when t equals 1/2, you're on the positive y-axis. Okay, t is 1/2. That means that the point on R of t lies above the point on of the circle on the y-axis, a distance of half a unit. So I'm saying that's half a unit. Now my scale in the vertical direction is not the same as my scale on the x and y. Just so we can draw this picture big without having the helix expand past the edges of the board. Okay, so there's 1/2 unit. Okay, so when t equals 1/2, again, cosine pi t plus sine of pi t gives you j. The j vector is from here to here, so that's where you are in the xy plane, and then you add tk, you go up half a unit. Now, when t is 1, that puts you over here at the negative x-axis, point in the circle on the negative x-axis, and you got to go up a distance equal to t, which is now 1. So you go twice the distance you did here. There's a distance, here's twice the distance. Okay, at t equals 3/2, you're above this point, and the distance is 3/2 of a unit. When t equals 2, you're above this point, 2 units. So you can trace out a curve that approximates the ellipse. And I didn't do a great job of that, but it's hard to make this thing look good. It probably looks better than it is. Okay. Now, I've sketched a couple of unit tangent vectors. Okay, here and here. Now, the unit tangent vector is easily calculated. I've said it before. It's in the direction of the derivative r prime, because r prime is the derivative, the rate of change of your position. And the position changes at any instant in the direction that the curve is pointing in that instant, but the curve in the direction you're moving, if you're moving on the curve. So you take that velocity and divide by its magnitude, you have a unit vector in the direction of motion. That's something you just need to intuitively understand if you don't already. Okay, then in this case, the magnitude, well, r prime is this. We take the derivative, we get pi from the chain rule, and the derivative is very straightforward. So the magnitude of r is what you see here. Okay, just square of this plus the square of this plus the square of the coefficient of k, which is 1. And just to be consistent, maybe I should write that as 1 squared. Now that's a bad 2, so who knows how that's going to be read. But it comes out square root of pi squared plus 1. So for this particular curve, magnitude of r prime is always pi squared plus 1. And the unit tangent vector is r prime divided by the square root of pi squared plus 1. Now between this point and this point, the unit tangent vector hasn't changed. Similar picture to the one I drew before, but vectors are in different orientation now. So there's your delta t, right there. Change, delta big T, the change in your unit tangent vector. The change in your unit tangent vector, if these vectors are very close together, since this is an isosceles triangle, it's very easy to argue that this vector is in the limit perpendicular to both of these vectors. Okay? The reason is you have here essentially an isosceles triangle, which means that the angle between this vector and the delta t is equal to the angle between this vector and the delta t. When the apex angle approaches 0, you have 2 equal angles up here. 3 angles have to add up to 180 degrees. As this angle approaches 0, these 2 angles have to approach 90 degrees. So you have perpendicular. You can also prove it, and I actually ask you to do that, by taking derivatives of this type of function. Well, the function we started with, just this function. Okay. From that, we conclude that t prime is normal to the curve, perpendicular to the curve, and then that the unit normal to the curve, and this would be our principal unit normal, our inward unit normal, is the derivative of the unit tangent vector divided by its magnitude. When you divide a vector by its magnitude, you get a unit vector, and you don't change its direction. So the direction is still normal, but now it's a unit vector. So there's your unit normal. Okay. Now let's see where we go. I think we go to the back of this board. And I should check to make sure the thing's still recording. Yep, see a red dot. Uh-oh. Better catch that before it damages furniture. Okay. We want to look, okay. Yeah, I think I commented. Previously, but I can do it here, okay. Something I wish I'd have said while I had the other board up there, but I don't want to flip it again. At least not while the camera's running. Okay, so let's go back to r of t equals cosine t pi ti plus sine of pi tj. But now we're going to do t squared k. We can project this vector onto the xy plane. It's going to project onto the unit circle, because projecting onto the xy plane just means that we ignore the k component, and we've got the unit circle there. And it's being traversed with constant period again. Okay? Constant period would be 2 units of time. So we have this statement. So here we are, t equals 0, and we come back at t equals 2, t equals 4, we're always back to this point, and between any 2 consecutive numbers we go around the circle 1 time. Okay, so that's this projected onto the xy plane. I just drew a small picture of that because I think everybody should understand that very well at this point. Now, if we want to project onto the xz plane, well, if x is toward you, y is there, and z is here, okay, you're looking at it from along the yz plane, so you're looking back at it here, and and I've kind of got the x-axis in the direction opposite that you would see if you're looking from y, but we're just going to have to live with that. At t equals 0, we get I plus 0j plus 0k. So that's just the I vector, and that's going to be the point on the x-axis. Okay, at t equals 1/2, at t equals 1/2, you've gone a quarter of the way around the circle, so you're now on the y-axis. Now if you're looking along the y-axis, that means it looks like you're just right in front of the z-axis at this point. Okay, then when t equals 1, you're at this point. Now what are the z-coordinates of these points? When t equals 1/2, t squared is 1/4, so you're up